Thank you for the introduction, and greetings there to Shanghai. It's the evening here in Seattle, Washington, United States, but it's not too late yet, so it's actually quite a good timing. So I want to talk about the future of Move, how we look at it at Aptos. My talk will be mostly language oriented, so I will talk about language features, not how you use Move at Aptos, on Aptos. That's covered partly by other talks. There will be quite a number of people from Aptos talking on this conference. I think after me is Tang. Victor will talk about gas. Sekun will talk about some very interesting operational and execution aspects. And Vanshan will talk also about very interesting things. So many of those talks will be in Chinese. So sorry, this one will be in English. Hopefully you can understand me. And I'm jumping in. Okay, so the future of Move at Aptos is bright. So that's what I would say. So we have quite a number of things in store for the language. So we want to add, just to give you a quick summary, and then I will go into the details later, receiver style function call syntax, real higher order functions, user-defined abilities or traits, a resource access control system, and last not least, enum types and public structs. And there are even more than features than I listed here, but these are the most important ones, which I want to point out here today. And just that you know, there's also a blog article about what I'm talking here about, came out in November or so. You can just Google it, like the future of Move at Aptos on Medium. You should be easily find it. All right, so before I jump into those various language features, let me say something about Move at Aptos in general. So what is that? And also what is the difference? I don't really want to talk a comparison here between Zwi Move and Aptos Move. That's not my job here, but there are differences, as you probably know. So Move is not exactly the same. So one important difference of Move at Aptos that we support basically the full language like it was originally designed without restrictions, which means particular including access to global resource storage. So from a Move smart contract, you can read and write to global storage at arbitrary addresses, provided the APIs allow you to do that. That's a little bit different than in Solana, where, for example, in Solana, in the account model of Solana, you need to declare what accounts you are going to access. In the Zwi model, you need to declare or indirectly declare via the objects of your transactions what memory you access. This restriction, if you think it's a restriction, is not in Aptos Move. This also means we support basically storage indirection. So by the way, I know this is a pretty much language-centric talk. So apologies if it's not that clear. So I'm mainly addressing here also language experts. But anyway, with including storage indirection, I mean, when you have a smart contract, you can read from storage some data. And in that data, you find an address for some other piece of storage, which you then look up with another operation in storage. Now, this is what I mean with storage indirection, sometimes also called secondary indexing. And this is a quite expressive feature which we support in Aptos Move. We also added in the last year some interesting features to the original Move definition. So there is the concept of inline and higher order functions, which is very popular between our users. And I will actually come back to that higher order functions a little bit later. And we also do support code upgrade. So you not just can deploy your new code at a new object or whatever, you can basically upgrade your existing code following certain compatibility rules. So Aptos on Move on Aptos is also characterized indeed, maybe more so even than the language, by a very rich set of framework libraries. We have quite a number of cryptographic utilities, and they are constantly growing. We have various collection types. So if you want to organize your data in collections, there are smart vectors, smart tables. These are basically dynamically growing data structures, which you can start small, but they can scale also to larger data storage. And last not least, we have objects and digital asset standards, which is a quite powerful abstraction mechanism, which is used throughout our library, basically in many places. Then the execution is kind of supported by features for parallelization. That is pretty important. So we have the so-called block STM or block software transactional memory, which is an approach for dynamic parallelization, where you don't need to know ahead of time which kind of storage is accessed by transactions. Instead, there is some speculative execution aspects. You just try to execute things in parallel, and if you detect read and write conflicts, then you will re-execute sequentially. And this block STM technology is quite powerful. There are a lot of papers, and it is the core of our current execution speed. We also have other interesting concepts. Sekun will talk later about those. For example, aggregators. Aggregators make basically the impossible possible. So you think that should be a parallel execution, a sequential execution, sorry, because it's like depending, you aggregate, you add something, for example, to some total coin value or so on, you think that must be sequential because that's how it looks like. But in fact, you can parallelize it. And as I said, Sekun will talk now about that. So that's the general picture about Move at Aptos. Now I want to go to the actual language extensions. But actually, before I go there, I want to say a little bit more why we are doing this. Why does Move need new language features? So this is a little bit, well, I mean, everybody tell you Move is a super great language. It's a fantastic language, and that's definitely true. But what has to be kept in mind is that when Move was designed at Meta, called Facebook at this time, the main objective of the language design was security. Security was all over the place. That's how the language is designed. That's how the virtual machine is designed. Developer productivity was not the highest priority when Move was developed. I can give you a very concrete example. If you know Move a little bit, there isn't, you know, there are multiple kinds of loops in Move. There's a while loop and there is an unconditional loop. But there is not a for loop in Move. You wonder, what the heck, why isn't there a for loop? Every language has a for loop. Well, Move doesn't have one. So we added one very recently, just basically a week ago or so. But this is the kind of developer productivity feature, which I mean, basically much more than that, not just the for loop, but simple things which you take without saying in other programming languages, which are actually missing in Move, because Move was designed with security first in mind. At Aptos, what we did in the last year is we didn't really change a lot of the Move language itself, because security was, again, our major priority. So we did a lot of work on Move-related security. There is a blog securing Move earlier from last year. Outlined some of those. We invented what's called the paranoid mode. We worked with consultants, security consultants like OtterSec, for example, together to figure out what is the best way to make Move super secure, because our main objective was to secure the assets on the blockchain, just like on the first bullet point here, security. But now, at this point, we feel we are a little bit more mature in regarding our security. So we have the blockchain running. We feel like more confident that everything is good. And now we think we are ready to evolve the language and bring more developer productivity. And that started for us with designing a new compilation framework, basically a new compiler for Move. I will only say that much about this. You may have heard about the Move Prover. The Move Prover is in a way also a compiler of the Move language. It only compiles to a verification system and not to some bytecode. And in reality, we had basically two compilers, the Move Prover and the Move compiler, because at Aptos, the Move Prover is very important for us. We didn't want to retire it, so we want to maintain both of them. But that was like quite a pain, because as I said, it's basically two compilers. So what we are doing right now, or nearly done with that, we're integrating the Move Prover compiler with the Move proper compiler, and then we have one unique compilation framework, and that one will allow us to extend the language with a high agility and high velocity in the next year or in this year. Okay, let me talk a little bit more about concrete features. So I start with some rather simple thing, receiver style function calls. So you may have seen already here in the middle of the slide where I'm going to, but the first thing you see there is the vector length function. So if you call the length function on a vector and Move today, in the normal style, if you haven't imported directly or used the length function, you would have to say vector column length. And then let's say you have a vector v, because this function expects a reference parameter to the vector, you also have to apply the ampersand to that parameter v. And yeah, why don't we just do v.length? No? So like if you work with any other languages, you are familiar with that notation. Many more program languages do exactly that. So it's a big shortcut. No? So you don't need to qualify the name because it's known from the type of v, that it is a length function, and you don't need to take that reference because the compiler can automatically determine that a reference has to be taken. So how does that work? I want to say only that much. So indeed, when we do this kind of extensions, we always want to be fully compatible to the existing language. So we don't want to break anything in the language. What we were going to do is a user can add or can name the first parameter of any function just self. And if the user use that naming convention, then this function can be called either with this dot notation like v.length, or it can be continued to be called in the old way. So this will allow us to basically add this self or rename this first parameter of all kind of functions in the Aptos framework to self. And whoop, you can use receiver style notation all over the place. Your existing code will not break and will still work without any problem because it's completely downwards compatible. So that's this feature. Then let me talk about the next one. So if you have used Aptos Move, you might have come along this inline functions which also allow function parameters. No? So for example, we have here this inline function contains, which checks whether inside of a vector there is an element which satisfies a certain predicate P. And this here is a notation of a function type. You know, the P is a function from the type T to the type bool. So this kind of higher order functions have been enabled in Aptos Move in the last year. They are very much loved by our users because they allow you to skip a lot of loops which you otherwise have to write. And for example, here's an example. So you check just for the contains of an element in this vector, which is greater 0. Now this bar x bar is the notation for a lambda expression. Okay, so that's a popular feature, but there are some problems with that. So one is basically that public inline functions can only use public accessors of their originating module. So that's pretty bad. No? So like they cannot access any private constructor or selectors or fields or anything like this. You would have to introduce, if you want to export an inline function from your module to be used by another module, you basically have to export also all the functions or make all the function public, which this inline function is using. This is not only cumbersome, it's actually also security concern because in Move, keeping things private to a module is one important way to ensure security. So this is not good. No? The other thing is this inline functions, you can easily get simply too large code if you inline too much, and then you hit some certain limitations, for example, the number of locals per function. So you hit a dead end, you can't inline everywhere. So what we want to do sounds actually rather simple for the user. Just don't have that inline anymore and just have fun contains, and that's now a regular function, a regular higher order function, like known for many other languages. How to do that, that's a little bit more complicated than the receiver style. We need to extend the Move VM by closures. We need to make that closure safe via a smarter and extended borrow analysis. So, but it's not rocket science. It's known how to do that from Rust, for example. But, and that's now specific to blockchain, we need to deal with reentrancy and related problems, because what higher order functions really mean is we're bringing also dynamic dispatch to the language. Dynamic dispatch is considered to be a bad thing. You know, probably heard about it, that in Solidity, a lot of security problems have been coming from dynamic dispatch via interfaces. But we have a way, which I will briefly talk about later, to make those dynamic dispatch with higher order functions or other aspects safe. Okay, so the next thing which you want to do is user-defined abilities. That is similar like traits in Rust, but it's basically hooking up on the existing ability system in Move. In Move, you already have abilities like store, copy, key, and drop. No? And we just add new abilities which a user can define. For example, the ability partial ordering. And this ability would mean any type which satisfies this ability has the less equal function. So we know there are very strong use cases in the Aptos framework to use that kind of abilities, for example, in the crypto space for crypto algebras, and also like for collection types, if you want to use ordering, ordered collections or something like this. And this will be enabled with this new ability type. but also you as a user can basically play around and build more powerful abstractions. What is under discussion right now is whether with the abilities, we also have interface abilities, so to say, which support dynamic dispatch. Most likely we want that. We have strong use cases for this as well. The interesting thing is, like I was already talking about dynamic dispatch, it's actually not something new from a security aspect, because higher order functions already represent dynamic dispatch, and actually abilities can be designed based on higher order functions. Okay, so let me quickly say something about access control. Because I'm a little bit short of time, let's skip this first example and just look at the second example here on the slide, which connects directly to the safety of higher order functions. So with access control, we add a new notation to the language, which allows you to specify which resources will be read or written or both. And this language is much more powerful than the existing acquire statement, the language for the access control. For example, it allows to represent negation. So we can basically say, hey, this callback function, which is like a dynamic dispatch situation, is not allowed to write to any of those resources which are stored under my contract address. Voila. So there is no dynamic dispatch problem. There's no reentrancy problem, because the core of the reentrancy problem is exactly that the callback calls again into the contract and modifies some state. So that's the way how we solve it. There are also other things about access control, which I skip here. There is an AIP 56, where you can read up more details. Maybe I point out there is one important aspect of access control. If you apply this access control on the transaction level, one interesting aspect is that you now have also the way to say this transaction only reads or writes to that memory. This is similar like Solana's account or Swiss object. And now you can do the kind of similar optimizations ahead of execution time for sharding or for parallel execution. Okay, so the last feature I briefly go over here are enumeration types. So if you know Rust, then you know what I'm talking about. We just want to have the same in Rust. But if you don't know Rust, just look at this simple example here. This is also called sometimes algebraic data type, by the way. This is such an enum type for a result of some function, and the result can either be okay, and then there is a value t, or it can be an error, and then there is a value e. So that's a typical example where you want to use that enum types, and then you will want to be able to match over those types with a match syntax, like in Rust, which we want to support. And you want to do that also outside of the module where the type is defined, which is something new. So you want to allow public enumeration types. And if you already have public enumeration types, you will also allow public structs. Okay, so what's next? Like I said, these features are enabled by the new compiler infrastructure we are building. So we expect that new compiler to ship in Q1. Initially, it will focus on compatibility. We may pick one of those features I discussed to make it more attractive to you users, but not all of those features I talked about will be immediately there. They will be added in the course of 24. I'm pretty confident if I would talk here in the next year on this event again, then these features will be all implemented during that point of time. Yeah, thank you. That's what I wanted to say. Thank you for your attention. And there are a couple of people on site. I think there is Ranshin and Sekun. If you want to ask them more things, they are probably happy to talk to you. Thanks.